So up next, we're going to look at oxidations, the reverse of reduction. And most of these reactions are going to be new to you. We're going to start off looking at kind of the most classic oxidations of all when it comes to organic chemistry, and that is oxidation using chromium-6 reagents. These are often collectively referred to as Jones oxidations. So let's take a look at some examples. Here I've got the booze molecule. I've got ethanol, and we're going to treat it with some source of chromium-6. That's chromium in its 6th oxidation state. And as you can see, it's going to oxidize that ethanol, that alcohol, up to a carboxylic acid. The functionalized carbon went from having 1 bond to an oxygen to now having 3 bonds to oxygen. So it was oxidized 2 levels, right? Now, let's take another alcohol. Let's take this isopropanol or 2-propanol. If we treat it with the same kind of conditions, a chromium-6 reagent, we actually get a very different outcome. Rather than going to a carboxylic acid, we actually end up making a ketone in this case. It's still an oxidation. That carbon went from 1 bond to oxygen to now having 2. If we now try this again on a 3rd alcohol, in this case we have 2-methyl 2-propanol, we get no reaction. Nothing happens at all. And at first glance, this looks really inconsistent. We have 3 alcohols, and we're treating them under the same exact conditions, but then we get 3 completely different outcomes. If you look for the pattern here, it's actually quite straightforward. This is what I want you to remember about your typical Jones oxidations. You're going to undergo as many oxidations on the functionalized carbon as there are hydrogens on the functionalized carbon. Look at this first example, the ethanol molecule. That is a primary alcohol. That primary alcohol, the functionalized carbon, it's in the 1st oxidation state, but that functionalized carbon has 2 hydrogens attached to it. That means it can be oxidized twice, once for each hydrogen. So that's why it goes from the 1st oxidation state to the 3rd oxidation state. And the simplest molecule that has that 3rd oxidation state through just pure oxidation is going to be a carboxylic acid. We're not introducing any other elements, no carbons, no halogens, no nothing, right? We're just introducing oxygens through this oxidation. If you look at the next one, we have a secondary alcohol. And the functionalized carbon has only 1 hydrogen on it, and that means it can only be oxidized once, essentially replacing that bond to hydrogen with a bond to oxygen. And that's going to wind up making, in this case, a ketone. All we've done is increase the number of bonds to oxygen without really introducing any other elements. And that's why this 3rd one does nothing at all, because that's a tertiary alcohol. And that tertiary alcohol, the functionalized carbon, has no hydrogens on it. And that means it can't be oxidized at all. So nothing happens. You just wind up getting your terbutanol back out again. This does mean that other functional groups other than alcohols can in fact be oxidized with chromium-6 reagents. For example, an aldehyde. An aldehyde, the functionalized carbon still has a hydrogen on it, right? And what I just told you was that these Jones oxidations, they're going to oxidize the functionality as many times as there are hydrogens attached to it. So if you have an aldehyde that's in the 2nd oxidation level, and because it's got that hydrogen attached to it, we can oxidize it once more up to the carboxylic acid. It's the same carboxylic acid we made at the top of the page here. In fact, that's kind of how that first reaction goes. Essentially, what we're doing here is taking that alcohol, ethanol, oxidizing it once to the aldehyde, and then that aldehyde is reacting and oxidizing further to the carboxylic acid. That's actually an interesting reaction because this is actually how vinegar is made, right? I mean, if you think about vinegar, where do we get vinegar from? And don't say a grocery store. Vinegar comes from booze, if you think about it, right? That's why we have things like red wine vinegar and rice wine vinegar. It comes from that kind of stuff. So if you wind up taking ethanol and exposing it to the right kind of bacteria, it can oxidize that all the way up to the carboxylic acid. That's why, beer goes skunky and things like that, or why it can give you a hangover, not the skunk factor so much. But if some of that ethanol gets oxidized up partly to the aldehyde, that acetaldehyde, I think I mentioned this before, is actually one of the things that contributes to giving you a hangover. Okay, if you try this same chemistry on a ketone, you should predict that that's not going to work. The ketone carbon has no hydrogens on it, so it can't oxidize. So if you dump a chromium-6 reagent onto, say, acetone, yeah, nothing's going to happen. In fact, Jones oxidations are almost always done using acetone as a solvent. Acetone is polar enough to kind of dissolve the reagents, but completely non-reactive, and it's got a low boiling point, so you kind of just evaporate off the solvent after you're done. Now, as far as what chromium-6 reagents are, they basically all form the same thing. This dichromic acid here, H2Cr2O7. Now, as far as I know, that's not something you can kind of buy. It may be actually quite dangerous. So what we do is we just make it in the flask, in the reaction pot. The most common ways that I've seen are to use a dichromate salt, like sodium dichromate or potassium dichromate, mix it with water and sulfuric acid. Another way to do it, which I've tried and have had no success with, is to use chromium trioxide, again under acidic conditions like with sulfuric acid. The sodium dichromate, potassium dichromate reagents work really well. They're salts. They dissolve really well in the aqueous media, and you wind up with these really, really brilliantly orange-colored solutions from the chromium. The chromium trioxide, it's not a salt. It's this oxide, and it just really is hesitant to dissolve, and just had no luck with it whatsoever. When you do a Jones oxidation, it's actually really kind of fun. It's really kind of cool, because the actual chromium-6 is, as I mentioned, orange in color once you make that chromic acid, that dichromic acid. And that orange color changes once the chromium does the oxidation. Remember, in a redox reaction, something's going to be oxidized and something's going to be reduced. So if you try to run this reaction on ethanol, the ethanol will be oxidized, and that means that the chromium is getting reduced. Specifically, chromium is going to drop from the oxidation state of 6 down to the oxidation state of 3. And chromium in the 3 oxidation state is actually kind of a bluish-green color. So when you run these reactions, it's actually really cool. What you do is you take your alcohol, dissolve it up in acetone, and then you sort of stir it and drip in your chromium-6 reagent, your dichromic acid, which is brilliant orange. And as soon as the first drop hits the solution, the reaction, it reacts the chromium-6, turning it into chromium-3, and it turns green. So you have these droplets of orange solution hitting the stirred mixture and turning green immediately. And then as you continue to add it, it gets greener and greener and greener until you go too far. Once you add one drop too many, once all the alcohol is oxidized and the solution is super duper green, you had more of the chromium reagent, which is orange, and it's going to stay orange because there's no more alcohol to oxidize. So now you have all this green chromium-6 floating around, and now you're adding, green chromium-3 floating around, and you're adding to that chromium-6 that no longer can be reduced down to chromium-3. And so the reaction turns this beautiful green color, and then you know you're done when it starts to turn kind of this muddy brown color, because that means you're now adding orange on top of the green, and it just looks like mud. So as soon as you start to see that mud color, you know the oxidation is done. All right, so we're going to look at a few special oxidations that are, some of them are related to the Jones oxidations that we just saw. The first one we're going to look at is another oxidation using chromium, using a special reagent called PCC, which stands for pyridinium chlorochromate, and I show the structure here. The PCC oxidation is special because it actually can stop at the second oxidation state. If you were to oxidize ethanol using just standard Jones conditions, chromic acid, it would go and oxidize twice, right? Because there's 2 hydrogens on that functionalized carbon. It would oxidize to the 3rd oxidation level, making a carboxylic acid. What's special about PCC is that it will stop at the aldehyde. And again, stopping at that second oxidation state, especially for aldehydes, is a really tricky thing, whether you're reducing or oxidizing. The thing with PCC is you have to keep it dry. I've seen textbooks and things like that say, it's PCC in dichloromethane or something like that, and that's completely unnecessary. While it's often done in dichloromethane, the real key is that you have to do this dry. Under dry conditions, the reaction will stop at the aldehyde. If you've got any water in there, what's going to happen is once the aldehyde forms, water is going to attack and add across the carbon-oxygen pi bond and actually make a diol. And because that is an alcohol, it will actually oxidize again to the carboxylic acid. But as long as you keep it dry, it will in fact stop at that second oxidation state. If you reacted something like isopropanol, a secondary alcohol, this can only oxidize once, right? It would naturally stop at the second oxidation state if you were to do a Jones oxidation. Well, that's going to happen here as well. If you do PCC, the oxidation here is going to stop at that ketone. In other words, for a secondary alcohol, you can turn this into a ketone either through PCC or Jones oxidations, because that's where it would naturally stop for a Jones oxidation anyway. A lot of times, people will, in fact, do oxidations of secondary alcohols to make ketones using PCC, simply because it's a little bit more gentle and it's not nearly as aggressively acidic as the Jones conditions. Jones conditions are pretty brutal. I mean, you've got that chromium-6 in there, which is toxic, although cheap, and highly, highly acidic from all that sulfuric acid. PCC, pyridinium chlorochromate, is done under dry conditions and pH not almost neutral. It's pretty close. So it's much, much more selective in the sense that it won't just shred all your molecules to pieces. Think about how many reactions we've seen that involve, say, water and acid or something like that. That's exactly what the Jones oxidation has. It's got a bunch of water and a bunch of acid, and it's going to react. It's going to hydrolyze things, whereas PCC is much more selective, much more gentle, so much more appropriate for more complex molecules. So that's the PCC oxidation. Up next, we've got the Swern oxidation. And this was one of the earliest reactions I ever had to run when I was in grad school. In fact, I think it was maybe the second reaction I ever ran. And I remember my mentor and a postdoc that was working in our lab at the time, they were talking to me in my mentor's office, and they were saying, oh, well, should we really throw him into a Swern oxidation so quickly? Because procedurally, it's actually quite complicated. So let's take a look what the Swern oxidation is. This was chemistry that was developed in the late 1970s. I've actually read this seminal paper from Swern. But here I'm going to take, again, booze. We're going to take ethanol, and we're going to treat it with some rather complicated-looking conditions. Starting off with, in this case, we have DMSO, dimethyl sulfoxide, which is weird because dimethyl sulfoxide is usually a solvent. It's a polar aprotic solvent. And in this case, it's not so much a solvent. It's actually going to be an oxygen source for our oxidation. So we've got DMSO, and then we've got this, if you look at it, it's sort of a diacyl halide. This is oxalyl chloride, born from oxalic acid. So it's the simplest of all the dicarboxylic acids, but now it's the acyl halide form. And you do this under cold conditions. You let that part react, and then when it's done, you treat it with an amine, most commonly triethylamine. And if you look at the outcome, it's exactly what the PCC oxidation did to a primary alcohol. It's special because it stops at that second oxidation state. It stops at the aldehyde. And yes, if you were to do this reaction on a secondary alcohol, it would in fact stop at the ketone. The Swern oxidation became a real synthetic big deal back in the 70s and early 80s because it was one of the first reactions for oxidation that was a lot gentler than the Jones oxidation and didn't have the problem of dealing with really, really, really toxic chromium reagents. It's procedurally very challenging, though, in terms of it's just complicated. It's also more expensive, but not wildly expensive. It's still a fairly inexpensive oxidation to do. Now, the Swern oxidation, I remember having to learn the mechanism of this thing, and it is kind of brutal. I'm not going to ask you guys to learn it. It's pretty long and not the most intuitive thing. But overall, what happens, just to give you an idea, is the DMSO and the oxalyl chloride react with one another to create the actual oxidant. The oxygen of the dimethyl sulfoxide attacks the acyl halide, displacing chlorine. Eventually, that chlorine comes back, attacks the sulfur, and displaces the oxygen, which is now attached to the oxalyl chloride, off. And you wind up with this sort of chlorinated sulfur reagent. Once that occurs, that's actually the oxidant. Then the alcohol attacks that, kind of does like a little SN2 type chemistry, and then ultimately the triethylamine removes one of the hydrogens from the carbon and then pushes off the chlorine as a leaving group. So that's where this actually comes from. It's a pretty convoluted mechanism, though, but that's where it is. And the Swern oxidation has had a bunch of sort of spin-offs that are also really synthetically useful, using slightly different types of reagents. I have a friend that works in the synthetic industry, and he was saying that most of the oxidations they do in industry are Swerns or Swern variants of some sort. But again, on paper, it really does the same kind of thing as the PCC oxidations. Another really special and kind of interesting oxidation is the Tollens oxidation. The Tollens oxidation is very specific because it only oxidizes aldehydes. So here I've got acetaldehyde, And again, aldehydes can be oxidized, right? You have that carbonyl carbon that has a hydrogen attached to it, so it can be oxidized once up to a carboxylic acid. And that's exactly what's going to happen. The reagents here are silver oxide under basic conditions, often with aqueous ammonia, and then you just treat it with acid to reprotonate the resulting carboxylic acid. It's a very special reaction because it only works on aldehydes. If you had a molecule that had an alcohol somewhere else, it would not oxidize that alcohol. It would only oxidize the aldehyde. The Tollens oxidation, I got a couple of little stories to talk about with that. The Tollens oxidation used to be an actual qualitative test for aldehydes. Back in the day, before we had modern spectroscopy like NMR and IR and things like that, structures were determined largely chemically by wet chemistry. So, and the Tollens oxidation was a way of confirming or denying that you had an aldehyde. What you would do is you would take the compound in question, treat it with the Tollens reagent mixture, and think about what's happening in that reaction. Where's the extra oxygen coming from in that carboxylic acid? It's coming from the silver oxide. And that means that the silver oxide, at the end of the day, is reduced down to silver metal, essentially nanoparticles of silver. And so that's how you can actually use this reaction to determine whether you have an aldehyde. You would take your mystery compound, shake it up with the Tollens reagent mixture, and if it deposited silver metal inside the reaction vessel, like a test tube, you would see this mirroring effect on the glass. And then you knew your molecule had to be an aldehyde because it's selective. It only reacts with aldehydes. In fact, this used to be how mirrors were kind of made, using this same kind of chemistry. I mean, mirrors were literally silvered with silver through this same kind of reaction. Nowadays, they use aluminum and slightly different kind of chemistry. But yeah, this is actually how mirrors were made. I remember several years ago now, maybe 5-6 years ago, I had won an award on campus, and I had to go to the president's house for a Christmas party, president of the university. And I was getting ready for it, and one of the students in my lab was saying, "Oh, you're going to this Christmas party you were invited to. You should take a gift." I'm like, "Oh, okay, if you say so." So I was trying to think of what I should take. So I came up with this really dorky idea of a Christmas ornament that was chemistry themed. So what I did was I just took a regular old test tube, like a 10 mil test tube, and did a Tollens oxidation inside of it. And so I silvered the inside of it, so it looked like a silver bell, right? It was mirrored. And then I had the student in my group just tie this like pretty little blue bow on it. I don't know how to tie a bow. I can do a Tollens oxidation. I can't tie a bow. And so we made this little Christmas ornament that was sort of chemistry themed because it was a chemistry reaction, a Tollens oxidation done onto a test tube. And she put it up on her mantle. Anyway, that's the Tollens oxidation. All right, so now we're going to look at oxidizing carbon compounds that are a little bit different. So far, all the oxidations we've looked at have had an oxygen in the actual functional group of the starting material. We've really only looked at oxidizing alcohols and aldehydes. Well, now we're going to start oxidizing some other things, starting off with alkenes. This is called dihydroxylation. Some people call it hydroxylation. But it's exactly what the name sounds like, dihydroxylation. We're going to add 2 hydroxy groups across a pi bond. So the conditions for this, there's a couple of ways this can be done. Here I've got this alkene, and I'm going to be treating it with KMnO4, that is potassium permanganate, which is actually one of my favorite compounds. It's not a very good reaction, in all honesty. I've done these before, and they're pretty clunky. But KMnO4 is the most intensely beautiful purple color you will ever see. And it's really intense. I mean, you can put like a couple of granules of this stuff in a gallon of water, and it already starts to look kind of a pinkish purple color. And it's fairly inexpensive as well. But yes, KMnO4 and cold conditions under basic conditions, and it adds 2 hydroxy groups across the pi bond. It's almost as though we added hydrogen peroxide across the pi bond, if you think about it. But that is an oxidation. We've increased the number of bonds to oxygen, in this case, on both of those carbons. Now, because this is both an oxidation and an addition reaction, remember, addition reactions, addition chemistry has a certain stereochemistry associated with it. You can either add groups onto the same side of a pi bond or on opposite sides, or a mixture of both. We call those syn and anti-additions. And it turns out that the mechanism for this kind of reaction results in a syn addition. Essentially, 2 of the oxygens from the manganese are delivered from that same manganese atom to one side of the alkene at the same time, and that's why it has to add syn. So it makes these vicinal diols through a syn addition process. Here, I'm going to show you a slightly different set of conditions, a more modern set of conditions. So I'm just going to use cyclohexene, and we're going to treat it now with osmium tetroxide, OSO4, and then a peroxide, hydrogen peroxide workup. There are some advantages and some disadvantages to these sets of conditions compared to the KMNO4. KMNO4 is dirt cheap, but the reactions are really poor. They tend to just turn these sludgy messes, the yields are crap. Whereas this osmium tetroxide reaction is wildly expensive and wildly toxic, but it works. And there are some modern variations on this that allow you to use a catalytic amount of the osmium and then a second oxidant as well, co-oxidant. So this is how a lot of this chemistry is done these days. But the overall outcome is the same. You wind up with a dihydroxylation. You wind up adding hydroxy groups up across a pi bond. But again, it's a syn addition. The overall process here, if you look at it, it has to be a syn addition for the same reasons that the KMNO4 variation of this had to be a syn addition, because both oxygens that are being delivered to the carbon species are on the same atom, the same metal, in this case osmium. And so they deliver at the same time from the same atom, and that must occur from the same face. The same chemistry can be done on an alkyne as well, except it happens twice, go figure. You wind up with two carbon-carbon pi bonds, and so you wind up adding essentially a hydrogen peroxide twice. You add an OH on each carbon and then another OH on each carbon. And it basically loses water and becomes a dicarbonyl, a 1,2 dicarbonyl. Two carbonyls right next door to each other. That's actually a really hard functional pairing to create. So if you ever see a 1,2 dicarbonyl synthetically, that's a good indication that you did some kind of an oxidation of an alkyne like that. But that's what you wind up with if you start to react an alkyne with these dihydroxylation conditions. All right, another reaction. We're back to looking at actual oxygenated species here, but we're going to be looking at more cleavage here. And this is not periodic cleavage, but per-iotic cleavage, right? Iotic meaning iodine. So here we're going to take a vicinal diol, a 1,2 diol, which we of course could have made through our dihydroxylation chemistry up above. And if you take that vicinal diol and treat it with a source of periodate, I've seen a lot of textbooks use periodic acid, but never in my life have I ever seen periodic acid. I have done this reaction and I've used sodium periodate. That's what I've always seen in the literature as well. But any source of periodate will technically do the trick. It's called cleavage because that's exactly what it's going to do. It's going to cleave the carbon-carbon bond between the two alcohols, and at the same time oxidize them. Those two carbons in the starting material are both on the first oxidation level. They both have one bond to oxygen. When the carbon-carbon bond breaks, we introduce a new bond to each, a new bond between carbon and oxygen, lifting it to the second oxidation level. So in this case, because my diol was symmetric, I end up with just 2 molecules of acetaldehyde as my product. And again, this works really well. It'll also work to make ketones. If instead of a vicinal diol that had both alcohols as, secondary, those two alcohols are secondary. If they were both tertiary alcohols, it would still cleave the carbon-carbon bond, but now you'd wind up with 2 ketones if you think about it, right? If these lower hydrogens were alkyl groups, methyl groups, then yeah, they're going to be methyl groups in the product as well, and that means they're going to make ketones. The overall reaction has a little bit of a quirk to it when you start looking at cyclic diols. If you look at this reaction I have below, I have these 2 different diols. The only difference is the stereochemistry of the diols. Here I've got a diol where the alcohol groups are in a syn or cis relationship, and then I have the same thing but now in trans. And again, you don't have complete free rotation in a ring. So the actual hydroxy groups are kind of locked in position. They can move, but they can't move 360 degrees. And it turns out that the cis diol reacts much, much faster than does the trans diol. And hopefully you can see what's happening here. Again, we're going to cleave the carbon-carbon bond between the functional groups and then oxidize both of those carbons up to the aldehyde, in this case, the second oxidation level. And the reason why there's such a difference based on the stereochemistry of the diol is how the reaction actually works. And again, I'm not going to show you the actual mechanism for this. I think it's beyond the scope of this kind of course. But essentially what happens, if you have an alcohol and you treat it with an acid, a carboxylic acid, we call that the Fischer esterification. It turns the acid and the alcohol into an ester. Well, there are other kinds of esters that exist. You don't have to just use carboxylic acids. If you use, in this case, a periodic acid, then you'll actually make this weird periodate ester. And that's exactly what happens. The periodate simply turns itself into an ester on both of those alcohol functionalities. And that can only occur really efficiently when those two alcohols are pointing in the same direction, because again, the iodine has to be, attached to both at the same time. So that's why the reaction is much, much faster when the alcohols are in a syn position rather than an anti position. All right, so now for one of my absolute favorite reactions of all time, ozonolysis. I mean, if you pick that word apart, you can probably figure out what this is going to be about. It's got the word ozone in it, so guess what our oxidant is going to be? Ozone. And lysis, meaning to lyse or cleave something. This is going to be another one of these cleavage reactions, except now we're using ozone to do the cleaving. This is a reaction on alkenes and alkynes, so we're back to carbon-carbon pi bonds. You take your alkene, or alkyne, but let's start with alkenes. You take it and you react it with ozone, O3. You do this under cold conditions because if you don't, it tends to explode. The overall reaction has a varied outcome depending on how you actually work the reaction up. So you introduce your ozone and then you quench it with, well, either an oxidizing agent or a reducing agent. The overall reaction is still an oxidation, but you can really, really oxidize it or you can sort of just partially oxidize it, depending on how you work the reaction up. The traditional ozonolysis typically uses this molecule. This is dimethyl sulfide. I've also seen zinc, and I've even done a variation when I was in grad school of this reaction that used triphenylphosphine, which you might remember from our Villiger chemistry. All three of these basically will spit out the same kind of products, though. In this exact example, we're starting off with this alkene. Now, look at it. Each carbon of that alkene has a carbon group attached and a hydrogen, and that's going to be maintained. What we're going to do is we're going to cleave the double bond completely and then introduce an oxygen atom onto each carbon, double bonded. So that means that if you kind of cover up half the molecule and replace it with an oxygen and then do it again on the other half of the molecule and replace that with an oxygen, you're going to get your product out of it. So in this case, we just made 2 molecules of acetaldehyde using that what we call a reductive workup. You can also use an oxidative workup. If you react with the same molecule here, ozonolysis, and now following it with hydrogen peroxide, it will actually oxidize it even further. Look at the products we got from the reductive workup. Those happen to be aldehydes, and we know that aldehydes can be oxidized. And that's exactly what the hydrogen peroxide is going to do. It's basically going to take it one step further and further oxidize those aldehydes up to a carboxylic acid, in this case, 2 carboxylic acids. And again, if you have a tetrasubstituted alkene, if you think about it, if you have a tetrasubstituted alkene, if those hydrogens attached to the alkene were in fact carbons, then there would be no difference in the products between an ozonolysis with a reductive workup versus an oxidative workup. Because the reductive workup would give you ketones, and ketones can't be oxidized any further. So it sort of just stops there. So yeah, if you use a tetrasubstituted alkene, it doesn't really matter what conditions you use. You're going to wind up making the same thing. You're going to wind up making 2 ketones. You can do the same chemistry on alkynes. It does cleave the carbon-carbon triple bond, and it replaces all 3 of the bonds of the triple bond with bonds to oxygen. That is, it lifts it to the 3rd oxidation level, and that would be the carboxylic acid. So we basically cleave it in half and oxidize both the alkyne carbons up to a carboxylic acid. Now, the reason this is one of my absolute favorite reactions is because I had to do it a lot when I was in grad school. On one of the projects that I worked on, I had to do a lot of ozonolysis reactions. In fact, I had tried the periodate cleavage reactions first, and they just weren't working out for me. But I was fortunate that when I was in grad school, our department had an ozonolysis machine. And it is a very special kind of an instrument, specific for this one reaction type. Ozone is really nasty stuff. I mean, oxygen itself, O2, is really, really reactive. You can spontaneously catch things on fire if you have a tank of oxygen and you spray it on like an oily rag or something like that. If you've ever worked in a hospital, they kind of make a big deal out about that. If you've got oxygen tanks around for delivering oxygen to patients and things like that, you have to be really careful with those tanks because they can just make things catch on fire. It's such a powerful oxidant. And ozone is even worse. I mean, ozone is aggressively oxidizing. Now, you can't just go and buy a tank of ozone. It's way too reactive stuff, and you wouldn't want to anyway. Ozone's extremely toxic, nasty smelling stuff. So the way this works, what we do is we actually take a tank of oxygen, O2, and we bubble the actual or pump the actual O2 through the ozonolysis machine. And basically what it does is it zaps it. It throws an electric spark across it. And that electricity sparking across the oxygen creates a very, very small amount of ozone. What you wind up with is a stream of gas that is mostly O2 with small amounts of O3 dissolved in it. And then this gas comes out the other side, and then you bubble that gas mixture through a solution of your alkene, let's say, and the reaction goes. The reaction has to be done really cold because as the ozone adds to the alkene, it makes these weird cyclic structures with 3 oxygens in them, and they're extremely unstable, and they tend to detonate if they aren't really kept very, very cold. So there was that factor. I mean, it was kind of cool because, it could blow up. Another thing that was really cool about it, though, was the color. Ozone has a sort of a bluish purple color to it. So here we go with the purple theme again. As you bubble ozone into the solution, well, nothing happens in terms of what you're looking at. Because what happens is the ozone, while it has this slightly bluish purple color, it immediately hits an alkene and reacts to turn into these cyclic intermediates that aren't colored. It's another one of these reactions, kind of like the Jones oxidations, that tell you when it's done. Essentially, you start bubbling the ozone into the alkene mixture, and every ozone molecule that goes in there and reacts with an alkene is immediately reacted away, and there's no color. But as soon as you add just a little too much ozone, if you've reacted all of your alkene and you continue to bubble the ozone mixture in, then ozone starts to build up in concentration in the actual solution. And because ozone has this purplish color, the mixture in the flask starts to turn purple. And it's a really nice color, and it tells you, hey, you've added enough ozone, stop the reaction. And then you just take it back, keep it cold, and dump onto it your workup conditions. So it's a really cool reaction. It, potentially explosive, turns purple, and you get to play with this giant lightning machine thing. We've got a couple more oxidations to look at. In fact, one of them you've seen before. Let's take a look at the Villiger oxidation. This one's an interesting one. The Villiger oxidation is typically looked at as a reaction of ketones. And if you think about that, ketones don't normally undergo an oxidation because the carbonyl carbon has no hydrogens on it, right? It's at that second oxidation level, and it can't go any further. And that's kind of what's special about the Villiger oxidation. It can go further. It's going to use a reagent that you've seen before. If you look at this is a per acid or peroxy acid. And you might remember we talked about peroxy acids when we talked about epoxidations. Regardless, the peroxy acid is going to donate one of its oxygens into the carbonyl carbon bond. It's going to interrupt, essentially, the carbon chain. It's going to break a carbon-carbon bond. In this case, we're going to turn this butanone molecule into ethyl acetate. And you see what happened there. We kind of inserted the oxygen, one of the oxygens from our per acid. We kind of inserted it between the carbonyl carbon and one of the alpha carbons. And it is selective, right? We've got 2 alpha carbons next to our carbonyl. And it's very selective in this case for going to the left carbon and interrupting that carbon-carbon bond. We, as organic chemists, call this migration. It's like the alkyl group migrated off of the carbonyl. And there is a tendency there for what groups will migrate more quickly that will allow you to predict the actual product made from a Villiger oxidation. So the migration trends are fairly straightforward. The easiest group to migrate, that is the bond you would most likely break and introduce the oxygen in between the carbonyl and that group, is actually a hydrogen. Now, that's kind of dumb because if you think about it, that means you're reacting an aldehyde, right? If you have a hydrogen attached to your carbonyl. And you're turning an aldehyde into a carboxylic acid. And there are just better ways to do that, like Jones oxidations. But it is technically true. So once you get past hydrogen, let's look at carbon groups. It basically comes down to degree of substitution. The more highly substituted that carbon is, that alpha carbon is, the more likely it is to be the one that migrates, or in other words, the one that gets the oxygen attached to it. So here, if you look at the example I have, the two carbons attached to the carbonyl. On the right side, that carbon is a methyl carbon. It's only bonded to, well, it's primary, but it's bonded to the carbonyl, and that's it, right? It's not bonded to any other carbon, so it's a primary carbon. Whereas on the left, that carbon attached to the carbonyl has bonds to two carbons. It's a secondary carbon. And since it's a secondary carbon, that's the one that prefers to migrate off of the carbonyl. That's where you insert the oxygen. And it follows basically that trend. Tertiary is faster than secondary is faster than primary, and primary is faster than methyl. Mixed into that is a benzene ring, which happens to occur between a primary and a secondary. And actually, that's not hard to remember, because if you think about it, aren't the carbon-carbon bonds in a benzene ring kind of like a bond and a half? Because of the resonance effect, right? It's not really alternating single and double bonds. It's actually, each carbon-carbon bond is actually kind of like a bond and a half. So it actually works out perfectly that way. So it's easy to remember. So I'm going to show you the mechanism of this. It's a little bit quirky, and in fact, it's somewhat reminiscent of the peroxy acid reactions we saw before when making epoxides. It's a little more intuitive, in my opinion. So if you look at it, we've got our ketone, and then we've got our peracid. We already know that ketones, being carbonyls, are very electrophilic at the carbonyl carbon. And if you look at the structure of a peracid, it's got that OH group on there, right? And that OH is my, an example of my class 2 nucleophile. It's got a lone pair and a hydrogen on the same atom. Kind of like water, right? So that's what's going to happen. We're going to have our OH group, the oxygen, attack the carbonyl carbon, nucleophile attacking electrophile. At that stage, a nonspecific base removes the hydrogen from the peracid. And then, well, we're going to kind of do a variation on acyl substitution here. The carbonyl is going to reform, and it's kind of, instead of spitting out a group, it's going to migrate one of those two carbon groups. This is where that whole migration thing comes in. So as the pi bond reforms, rather than kicking off a leaving group, what happens is the carbon group that was attached originally, the one that is most likely to migrate according to our trend up above, migrates from the carbonyl carbon over to the oxygen that just attacked. When that occurs, you exceed the octet on that oxygen, which then pushes off the other oxygen. And if you look, that other oxygen is actually a decent leaving group because that is a carboxylate. It is a resonance stabilized anion, and that's kind of what drives the reaction here. So it's a very simple mechanism, right? It's just 3 steps. The OH group of the peracid attacks the carbonyl. We've seen that before. It's the first step in acyl addition. We deprotonate with a nonspecific base. And then the carbonyl reforms kind of like an acyl substitution, but rather than a group leaving, one of the carbon groups migrates to the oxygen that just attacked, which then expels out the other oxygen. The net reaction overall typically turns ketones into esters. And it's a special reaction for that. It's weird because you don't normally think of ketones as being able to oxidize. And it also breaks a carbon-carbon bond. Looking at these oxidations, we've seen a lot of examples now of carbon-carbon bond breaking reactions. By Villiger, peridate cleavage, ozonolysis, and we've had a few others as well, like the haloform reaction. So yeah, just another oxidation that actually ends up breaking a carbon-carbon bond like this, making esters. And then just to remind you, yes, we also talked about peracids reacting with alkenes to make epoxides. And that reaction, if you recall, is in fact stereoselective. If you wind up starting with a trans alkene, you're going to wind up with the alkyl group's trans in the product as well. The most common peracid that you often see is MCPBA, metachloroperoxybenzoic acid. And it's just the most common one you'll see. If you look in textbooks and things like that, they'll almost always just say MCPBA rather than a generic peracid like that. All right, so as far as oxidations and reductions go, that's it. You're going to see that these reactions are going to be really useful when we start looking at our next topic, which is all about new and powerful synthetic strategies. Basically taking this information coupled with all the reactions you've seen over the last 2 semesters and really utilizing it to approach synthetic problems in a different kind of way. Because you now know so many reactions that it can get a little bit muddy when you're trying to approach a synthesis question. So what we're going to do is try to get you out of that mud a little bit and give you some better strategies for actually tackling synthesis problems.